Hello everyone, this is Saima, and today we are going to learn the concept of derivative. Well, you are likely already familiar with the idea of slope of a line. All it is like describing the rate of change of vertical variable with respect to a horizontal variable, right? So for example, here I have the y-axis in the vertical direction and x-axis in the horizontal direction. And if I wanted to figure out the slope of this line, okay, I could pick 2 points, these two blue dots, this one and that point. I would say, okay, from this point to this point, what is my change in x? Well, my change in x would be the distance right over here, okay, mhm, which will be the change in x, okay. We can see the small delta x here. This is a Greek letter, which we call delta, which is actually a shorthand for change. So change in x. I could also calculate the change in y as well. Mm. So this point going up to this point, or change in y would be this right over here, or change in y. We would define the slope, or like we have defined the slope, right, as change in y here over change in x. Here I have written this slope of this line would be the change in, sorry, this is change in y with respect to change in x. I have taken the written change in y with respect to x. It should be the change in y with respect to change in x. This is what we call or slope. Okay, so yeah, okay, this is also described as the rise over run. Okay, and for any line it is associated with a slope because it has a like constant rate of change. If you took any 2 points in this line, no matter how far or no matter how close together, the slope will be same anywhere. So if you were to do this calculation, you would get the same slope. Okay, that's what make it a line. So, but what's fascinating about calculus is that we are going to build a tool so that we can think about the rate of change, not just of a line, which we have called a slope. We can also think about rate of change, the instantaneous rate of change of a curve, like this curve, of something whose rate of change is possibly constantly changing. Okay. For example, let's take the example of this curve where rate of change of y with respect to x is constantly changing. Mhm. Even if you want to use our like the traditional tools, if we say like, yeah, we can calculate the average rate of change, let's say, to from this point till this point, for example. Okay, uh, would be the slope. Okay, the slope of this curve would be the slope of the secant line that connecting them. Okay, like we can, oh, sorry, it's not straight that much, but there should be a secant line. Okay, so it would be the slope of this secant line. But if we pick two different points, we pick this point to this point, okay, the average rate of change between these 2 points will all of a sudden looks quite different, like from here to here, okay? It looks like it has a higher slope. So even when we take the slopes between 2 points on a line, the secant lines, you can see that those slopes are changing, okay? But what if we want to ask ourselves an even more interesting question, like what is the instantaneous rate of change at that point? So, for example, how fast is y changing with respect to x at exactly at that point, at a simple point like this point? Okay, yeah, and when x is equal to that one, let's call it as x1, x1, like this thing. Okay. Mm. Well, one way you could think about it is, what if we could draw a tangent line to this point? Okay, a line that just touches the graph right over here, and we can calculate the slope of that line. Well, that should be the rate of change at that point, like the instantaneous rate of change. This is what we call the derivative, like um, a rate of change of y with respect to x when the change in x is approaches to zero. This is actually the concept of derivative, and we call it as dy by dx.